Okay, so in Unit 3, in Conservation of Energy, we talked a little bit about elastic collisions. And in elastic collisions, we said that mechanical energy is conserved. But I also gave you an introduction. I said that in any collision, momentum is also always conserved. So 9.5 is about inelastic collisions. And I did talk about these in conservation of energy, but these are the hit and stick collisions. So an inelastic collision is a hit and a stick, which means that the objects move together with one shared common final velocity. So we're going to take a look in this section about how we quantify that. So a perfectly inelastic collision, so meaning perfectly inelastic, is when two objects do hit and stick together and they have a common final velocity. For example, we could have clay hitting the floor or a bullet embedding itself into wood. These are collisions where the two objects essentially become one. Now, it's important to note from last unit that when this happens, mechanical energy, we talked about before, it's the sum of kinetic plus potential, is not conserved. Anytime that two objects hit and stick together, there's some energy that's automatically lost due to thermal energy, due to the rearrangement of molecules in the collision, no matter what. So we cannot say that the kinetic energy of this guy plus the kinetic energy of this guy equals the kinetic energy of the final. It doesn't work that way. And what's worse or harder is that when they go in different directions, kinetic energy doesn't help us anyway, because kinetic energy is not a vector quantity. So we got to keep those in mind as we're solving problems in this section. So here is a quick check. We got two boxes are sliding along a frictionless surface. They collide and stick. What's the velocity afterwards? Well, here I have 4 kilogram meter per second. Here I have 4 kilogram meter per second. Oops. So when they hit and stick together, I have a positive 4 and a negative 4, and we're going to come to rest, actually. We're going to perfectly come to rest at the end of this collision. So we actually looked at the result of this problem and evaluated it further in conservation of energy, but this is the problem where we have two train cars coming together, and I know the mass and the velocity of the first train car, and I know the mass of the second train car, and I know the final velocity of both the train cars. And my question is what was the initial speed of the heavier car, of this cart 2 over here? And we can use conservation of momentum, that PI equals PF, to solve that problem. And this is an inelastic collision, so it's a hit and stick. So anytime that I have an inelastic collision, I have the mass and the velocity of the first object initially. I have the mass and the velocity of the second object initially. And those two objects are going to come together, m1 plus m2, and have some shared final velocity. So we'll be using this variation of the conservation of momentum as we solve these problems. So here's another partner problem, same concept, except it's a little bit more tricky. The bullet is fired into the wood where it lodges, and then it slides across the floor. What was the bullet's initial speed? This is actually a really complex problem because we're going to have to use a little bit more with forces, with this friction concept here, to solve for the acceleration of the block. And knowing the acceleration of the block and the distance it traveled, I have to figure out its initial velocity. And then once I have the initial velocity of the block with the bullet together, I can use conservation of momentum to figure out the firing velocity of the bullet. Holy cow. Yeah, we're going to go through that one during class. It's a complex one, but it's a good problem. But that's actually your quick little introduction into inelastic collisions. So again, the biggest takeaway for that, momentum is of course conserved, but I have some initial momentum for the first object, some initial momentum for the second object, and those two will share a common final velocity. And if I use the problem in this manner, that's the easiest the easiest way to set it up. And it's just a variation of the conservation of momentum, but it works pretty well. All right, we'll see you in the next segment.